Hello everybody. We've been working on calculus drills using Maxwell's, and now we're going to use that basic physics to get into electrical engineering. And today we talk about bandgap theory, and this is the basic of the semiconductors. And the semiconductors, the first one we explain is a diode. Today I hope we get to that, and after diode, next videos we talk about bipolar and MOS, and following videos show how to design the circuit and the logic circuit, analog circuit. Then later on move on to the logical design. Logical design is translated into the circuit, and that's the logical design will make it possible for you to design IC chip. Okay, so this is a long trail of the videos. Please register and keep yourself in, because depend on my time's availability, I keep issuing the video from basic semiconductor theory. Bandgap theory is the basic theory. From there to all the way to device and the circuit and the logic. Okay, so make sure you put yourself into the registration list. It's going to be a long series, and I try to put out the video as many as possible. Depend on how much time available. Now, the bandgap theory, you often see this kind of diagram, and let's understand this first. The metal semiconductor insulator. Insulator is like a plastic. Okay, the metals has a valence band. So what is a valence band? The valence band is something like you have an atom and electrons around. Okay, and when it's crystallized, this electron is used, the valence electron, that means it's used to connect this atom to atom. Okay, for example, in the carbon you have 2 2 2 2. You may have a H, right? The H 2 electron in the lowest orbit is stable, so you can have hydrogen around, and you can have O, so and so. This electron, the role of the electron is called valence. The valence means you satisfy the orbit requirement to be stable, and that's gonna make a connection between atoms. The crystal is connected by valence. Okay, now there are more orbit. Let's use a different color. More orbit outside, and electron is sometimes particle, sometimes the wave. Okay, so it's tricky when you talk about the electron in the material, the bulk. It's you have to use wave characteristic and particle characteristic sometimes. Metal like a copper has a lot of overlap in the orbit. It doesn't mean there is an electron. Okay, but this overlap is crucial for conductivity. When you talk about conductivity, the nucleus is vibrating by temperature. Temperature is a key factor, okay? And sometimes that vibration give energy to electron, and electron go up to the upper orbit. This orbit is overlapping, so it can move around all the way from one side to another. Electron freely move. It's called free electron. Okay, so if you look at the copper conductivity curve, when temperature is low, conductivity is low, it suddenly goes up really high. So it's a conductor. But beyond a certain temperature, it goes down and doesn't go. Why that? Well, it generates a lot of free electron and conductivity increase, but mobility decrease, because when atoms start vibrating much harder by temperature, then electron is not easy to move around because it's act as a resistance. So mobility is related to resistivity. Okay, so there are several factors for conductivity. Free electron, you have a free electron, then its conduct amount of free electron decide how much it has conductivity. But the certain point the mobility become dominant, then this decide the conductivity, limit the conductivity, and the resistor made on the IC chip has this mobility. It's limit the mobility of electron from one side to another, and that's why you have a resistor R. Okay, so there are several other factors to affect the conductivity, but mainly we concentrate on conductivity. Its conduction band. Okay, so insulator is like plastic. You have a carbon atom like that, long molecule. There's no overlap on the carbon from here to here. Distance is very far away. Okay, so the valence band, electrons around the carbon here, and conduction band is very far away. So the energy need, the voltage or phi, either way, need is very big. Okay, and typically it's like a 4 electron volt or more. What is electron volt? Electron volt is 1 volt potential move 1 electron. That's amount of energy. So the electron hardly jump over here and jump over here. Okay, so it's going to be it's total insulator. And suppose you have conductor here and plastic film is pasted on the conductor. Electron can be injected here, so you have a carrier, but it's stuck here, and some maybe move when you increase the volt, like 1000 volt. It's forced to move to the nearby atoms, but certain layer has so-called space charge, and the space charge is something like, even you have a conductor here, if you have a space charge formed here in the bulk, and this layer, remember, divergent E equals epsilon. The very strong electrical field is generated against this electron. So you put the negative and the positive, you try to inject the electron, which is a carrier. You need a carrier for conductor. The carrier cannot be injected beyond a certain point when space charge builds up. The space charge generates electrical field against the electron. So even only 4 electron volt material, sometimes you need 1000 volt to inject some charge. Okay, so this is the insulator. So insulator sometimes not only just the distance between atoms, but any charge accumulated here is going to form the wall, very high wall of potential. And you know the Maxwell's equation, the charge is gonna generate electrical field, and in this case against. What's happened to the positive side? Well, these plastic molecules, electron is sucked out, but this form positive space charge. So this side also, it's very difficult to suck out more electron, because when this positive, if electron move from here to here, then this move continue. Okay, so the positive charge, actually it's not positive, it's a lack of electron. We call hole in semiconductor terminology. What is a hole? Hole is electron move away from the orbit. So you have a one space for other electron to move in. And this can be the carrier too, because when you take the electron, you can move electron from next door neighbor and move from next door. So as a result, it's equivalent to moving electron all the way here. Okay, so remember, carrier, you can consider electron and the hole, electrons and the holes. Okay, now going back this energy level. This energy level, what is this bottom energy level? It's a nucleus, the basic orbit, and orbit distance. Okay, the energy increase as orbit distance increase. So you have to think this way. This band gap diagram, it's showing the energy, but energy actually is the orbit distance. Okay. Now, semiconductor it's a half conductor. The reason is you have like a silicon crystal, right? That's a basic material for IC chip. Energy level, say this is a silicon and a valence band orbit, and this is higher orbit, and usually electrons here when temperature low, and when temperature gives the energy to the electron, it may jump up. So there is a gap between, and silicon crystal is about 1.1 electron volt. So what does it mean? Certain temperature, it take a middle point, and that's called Fermi level. Okay, and say this potential measuring from nucleus to outward. Okay, this is valence, limit of valence. This is the free electron. You can freely move around from silicon atom to silicon atom, right? We take this Fermi level in the middle when electron is excited by accepting energy from nuclear vibration. It jump up to here. If energy level this much, then electron has this almost 50-50 chance to go up by acquiring more energy, or drop down, go back to lower orbit and settle there. In this case, it doesn't move. The valence band, no carrier. Okay, now in the crystal, the electron is very orderly. When this guy moves to the free band, there is a hole. So when you have electrical field applied this way, this hole can accept another electron here, right? So the electron move this way, the hole move this way. Okay, so this is the basic, the band gap when electron jump out to the free electron energy, then electron move along the electrical field, the hole move other way. Okay, so how many carrier exist? Okay, the say we call electron carrier, usually use N, and the hole is P. Okay, so this is a basic experimental this is it's the intrinsic, the amount minus E free minus E Fermi. This is free, it's not good. It's conducting. Let's make it C. Okay, minus over K Boltzmann constant temperature. Okay, this is like silicon. The conductivity goes up with temperature and the log scale, and this log scale become E. P is P and P, E minus EF EC KT. Okay, so this E energy over KT become very basic equation for semiconductor. It's bipolar, MOS, everything. You have to remember this. Okay, so energy level over KT. This is the energy difference. This energy difference and energy difference. Okay. Now, assume it's intrinsic. Intrinsic means silicon only and perfect crystal. We take a geometric average, and this one is going to be N and P and E minus conductance and valence KT, right? So geometric average. Why geometric average? Because the log scale. You don't do A plus B over 2, this kind of average for log scale. Log scale, you have to do multiplication, geometric average. So this is going to be N and P E minus energy gap, right? KT. And this N, average N, is going to determine conductivity. So temperature curve of the silicon and the conductivity become like in log scale like that. Okay. And here important thing is you have an energy gap. This energy gap in the silicon is about 1.1 electron volt. And this carrier determine conductivity. Carrier determine conductivity of silicon, intrinsic silicon. Okay. So far okay. This is an energy band gap amount determine the conductivity of silicon, and we're going to manipulate this band gap in order to create P-type silicon and N-type silicon. They are called extrinsic silicon, because silicon has some impurity like a boron and others. So what happens if you put the say boron? You look at the periodic table, boron, carbon, this is just here in the middle, right? And aluminum, silicon, and phosphorus, and gallium, germanium, and arsenide. And this is 3. That means electron, only 3 electron on the orbit. And this is 5. It's a 5 electron on the orbit. What happened is, when you mix, say, boron, so boron is inside the silicon crystal. This one orbit has a hole. Okay. So this is gonna be, we call P-type. Now if you put phosphorus, like a phosphorus, silicon, make a crystal, then you have an extra electron here. It's called N-type. And this is very important to make a MOS, of course, diode, bipolar transistor, everything. Now, extrinsic semiconductor, the band looks different because intrinsic Fermi level is right in the middle, right? But by introducing impurity in the crystal, Fermi level shift upward or close to valence band. And what does it mean? The Fermi level change means carrier density N and P change. How much is change? Okay. Needed some coffee to talk about this kind of things. This impurity, the density, the electron carrier and hole carrier, the density created by impurity is far greater than intrinsic carrier generated purely by silicon and temperature. Okay, so you can ignore this and deal with only amount of impurity, and that determine it's become more conductive. Yeah, because you introduce a lot of carrier, so it's much more conductive than pure silicon. But conductivity is different. N-type, when you put voltage, then electron running all the way, a lot of electron running all the way, and that's determining conductivity. P-type, so many hole, so electron run this way. This is negative, okay? So conductivity increase a lot. So how much it's increase? Okay, so coffee time is over. Actually, how do we introduce the impurity to make N and P type? Well, they use a glass tube and put the silicon and heat up, and if it's phosphorus, the gas phosphorus or boron, the gas go through this tube. Then this silicon, because of the heat, the molecule vibrate, and while molecule vibrate, the boron diffused in and replace silicon. So we use a diffusion process. Okay, so when we make a device, for example, diode, we have a silicon, we diffuse, say, N-type impurity all over. Then later we diffuse P-type impurity, right? So we diffuse up to here, So there is the impurity boundary where this side is all p-type and this type is n-type. So we call that the junction. And in this case, we slice this silicon, make one piece diode. It's a P and N. And we put the lead. So that's the way how we make a diode. And transistor, we talk about this in detail later. It's MOS and bipolar, the basic method of diffusion. But diffusion is a slow process. So I think in order to speed up, implantation method is used this day. So you have a silicon, you hit, say, phosphorus atoms, then it's go inside like this. Then you use a heat annealing process. Means this one is kind of very violent way of phosphorus atoms here. Crystals, this structure is broken, but when you heat up and slowly cool down, then this gonna go to the right position and become like a very organized crystal with impurity. So this implantation method is also used. In the process of silicon wafer, this is the ongoing technology, and when it's go to 7 nanometer to 3 nanometer, the different method is used. You have to invent the better process to make a device. So this is whole another subject of how to make it kind of discussion. Okay, so we go back to the equation we got here. This guy, the average, let's write it here again, NC and NV, and minus EG KT, right? So when you drive the impurity in, the intrinsic material NC equals NV, because the single electron jump out to the conduction layer, then single hole is created. So it's always like this. Okay. But when you have, say, extra electron in a crystal, you have the carrier provider, donor here, very close to conduction layer. So a lot of carrier is generated. This is the N-type. On the other hand, P-type, you have the holes
here, and the holes help carrier to come in, and this carrier move is going to be the hole move, the opposite direction. This is p type. So we define Fermi level as the just 50-50, equivalent position energy wise. Either go to conduction layer or go back to valence layer. This Fermi levels change by introduction of the impurity. So okay, so going back to this, we know an average, right? And suppose Fermi level change. It was average in the middle, right? And suppose it's moved up this much, and that's, say, it's Q phi. Okay, that much energy change, and this QE is going to be new Fermi level minus E average. This is the average in the middle. This average is EV plus EC over 2, right? So this much change, then when it's a donor means donor of electron, is provide the electron, we say ND. This much the impurities introduced, how much Fermi level change, the amount its change is N average E Q phi over KT. If it's acceptor is a whole, then it's a P, this is same as N average, E Q phi KT. Okay, so we know, depend on how much we introduce, either N type or P type. If you introduce both and almost same amount, then it doesn't become N type or P type. It's become more conductor, right? So N type, this is the equation. P type, this is the equation. The relationship between impurity and Fermi type, Fermi potential energy change. And also we have to know this whole mobility is much smaller than electrons mobility. So if you have a diode N and P, so what kind of characteristic it's going to be for forward voltage? Okay, this N type is going to dominate, right? Most of the current is pushed by N type, and the P is act like a resistor. Mobility is low. So N type equation, the this guy. So the diode characteristic, if you look at the voltage, if you apply voltage in the current, it's going to be exponential because of this. And this exponential, there's a constant, this impurity amount, ND. Depending on how much ND, the Fermi levels change. So exponential curve is going to be depend on the amount of impurity. It's just for the characteristic is going to be exponential. This is diode. Okay. What's happening if you put reverse voltage? So all the electrons go there and the holes go there. There is a space called diffusion layer. Around the junction. And what the diffusion layer is basically around the junction, the electron disappear and become plus, and the other side negative. So if you write the Fermi level P type, N type, it's going to be and this is a Fermi level, the P-type Fermi level and N-type Fermi level. And this is the line. So in this area, there will be diffusion layer. Means it's charged opposite polarity. Okay. So from this equation you can get the phi, and this 2 phi, this is the potential difference, is gonna be, this is phi 1 phi 2, phi 1 plus phi 2, and that much the voltage is sustained. That means it's balanced. This voltage, external voltage, is V with this diffusion layer's potential. What's the potential profile? It's a Poisson's equation, right? ND and KT. Now this NA and ND practically it's either this way or this way. Okay, either P-type or N-type. And this Poisson's equations, if you solve the one-dimensional, it's going to be this density, whatever the density low, sorry, this is this one, not the K. and this one is going to make this width. It's determined. The phi determine this width with x. Okay, so depend on the voltage, the width increase when voltage increase, or this diffusion layers become thinner when voltage decrease, and that's why it's go like this in the diode. This act on voltage applied. So voltage, you apply voltage is 5 volt, 10 volt is a negative. Okay, then this guy is diffusion layers stop current flow, and this create this diode characteristic. Okay, that's all for this video. And another important thing, the next time we talk about is, then what is this diffusion layer? It's act like a capacitor, and this is the cause of all the stray capacitor around the transistor, and even MOS. This the stray capacitors existing. This capacitor is a cause of switching time delay, and this very important to reduce this capacitor in order to have a fast switching transistor. Well, that's gonna be the next video subject. So we get into the device, transistor, and the switching gate circuit. We are going to go very fast from device characteristic to device and circuit design, and circuit design to logic design. Okay. If you think this video was good, please click likes and put any comment below. When I have a time, I will respond. Okay.